Hey guys, what's up? Welcome back to Classroom. It's Mr. Low, and today we are going to finish discussing on worksheet 18.3 in our preparation for the weighted assessment. Alright, so this chapter I think is pretty simple, pretty direct. It's just chemical reactions and how to write chemical equations, right, for reactions concerning acids. Right, we've learned three different reactions with acids, namely with metal, with carbonate as well as with alkaline. So I think your job here is to remember what are the products that come out um, from each reaction, and particularly how to name the salts that depends on what acid and what alkaline, for instance, that you put in. Yeah. So for worksheet 18.3, as I was saying in class, is that this is the kind of question that requires you to do a bit more thinking instead of just regurgitating some known facts, and hopefully that the way that you write it suits the teacher's taste and preference. No, of course not. I'm just joking. So let's dive right into it. Okay. So for this question. This question is stated question 2 or on mine on my Word document, but it's supposed to be question 1. Yeah. Okay, so a base thing has a pH lower than 7. So immediately when you read the question, you should be highlighting and noting down what this means to you. Well, what does this mean to you? pH lower than 7. Well, clearly it is acidic. Right? Okay, next. A wild thing on the other hand has a pH of higher than 7. So this is the exact opposite. Then this is alkaline. All right, so the question continues. This poor Isaac was stung by a bee. All right, so particularly stung by a bee, not a wasp. All right. Now this Gino, I don't know how this Gino is related to Isaac, probably a friend. Right, Gino applied vinegar on the sting to hopefully help Isaac. Ah, what a great friend. Didn't even bother to Google um how to treat a bee sting, right? So anyways, he was trying to help, no problem there, right? So I assume Gino is a guy. Anyways, so one is wrong with Gino's action and why, right? So this type of questions typically, as you can tell, is 2 marks. 2 marks, 1 mark for what is wrong and 1 mark for the explanation. All right. Okay. So if we look at the bee sting, it has pH of less than 7, which is acidic, and we do know also, from the lessons and probably from your experience, vinegar itself is also acidic. Okay, it's weakly acidic because it tastes sour. If you have tried before, if you haven't, you should. So, what's the explanation here? Um, of course, it's wrong because the bee sting, right? The sting of the bee is acidic. Okay, vinegar is also acidic. Yeah. So therefore, applying acid to acid, there is no reaction, right? And so therefore, it doesn't neutralize the bee sting. Right. So for bee sting and wasp sting, which part of it is acidic is probably the toxic portion, right? The toxins. So if you happen to get a bee sting, there are certain toxins which may not kill depending on what bee is. I'm not too sure, right? But the way to go about treating it is, well, applying some alkaline because it's acidic, right? Hopefully to neutralize the toxin, right? Next, if Isaac was instead stung by wasps, so remember a wasp sting is alkaline, okay? So would this action help? Then, yeah, of course it would help because it's the opposite of a bee sting. Okay, a wasp sting is alkaline, so it would possibly react with the vinegar, which is acidic. Yeah. Okay, I'm not gonna pause to let you copy down the answer. To take down your answer, please mark and do your corrections. Okay, you can pause the video at any point in time to mark your answer and take down the correct answer. Okay, next. Yeah, antacids relieve gastric pain caused by high stomach acidity. Yep, so we've discussed this in class before. Alright, so stomach acid is hydrochloric. Okay, so to relieve gas pain caused by hydrochloric acid. So as you can tell, this antacids probably serves to get rid of the acid. Yeah, no other ways. Okay, so some antacids contain hydroxides, metal hydroxides. So immediately when you see the word hydroxide, you know that you are looking at alkaline. Of course, it makes sense, right? To neutralize or get rid of the acid, you can use alkaline, of course. Such as aluminum hydroxide. This one example. Other types of antacids may contain metal carbonate. Also, this is the interesting part that some of you are asking. How is it that metal carbonate can help to solve the problem? So anyways, I'm gonna just write down this is a carbonate. Okay, so immediately when you see this thing, you should be thinking of the reaction between acid and alkaline, as well as acid and carbonate, simply because we are swallowing these two things, essentially dumping carbonates and alkaline into our stomach filled with acids. Yeah. Okay, so how do you think these antacids containing metal hydroxides in particular, we're looking at hydroxides only, work to relieve the gastric pain? So essentially, the question goes like, how does the alkaline get rid of the acid? So this is something that we are familiar with. Okay, metal hydroxide is alkaline, reacts with the acid in the stomach to neutralize it, thereby relieving the pain. Okay, this is pretty straightforward. And this is I mean we should be we can use the word neutralize and encourage to use the word neutralize, because well, this is acid alkaline reaction. All right, next. So how do you think antacids containing metal carbonates now? We are interested in looking at metal carbonates now. How does it help to relieve gastric pain? Okay, so here we must, in case some of you didn't catch it during class, let me just write it down by the side. You should be actively thinking of how acids react with metal carbonates. Okay, so I'm writing it down here. So what does it give us? Remember, we do not write equal sign for chemical reactions. We write an arrow, right? So this gives us a salt plus carbon dioxide gas plus water. Okay, please write in full in exam. Spell it out full. Do not write chemical symbols. And leave the chemical symbol problem up to, for upper side. All right. So yeah, you can see that acid here. Well, it's acidic, of course, in nature. Okay, metal carbonates essentially actually carbonates are salts, so they're kind of neutral. So on the left hand side of the equation, overall you have some acidic stuff, which is because of the stomach acid. But if you look at the products at the end of the day, all these guys here are neutral. Okay, these guys are neutral here. So you can imagine, my stomach is full of acids. The pH is pretty low, right? So if I dump enough metal carbonates into the acid, over time, if you put in enough, the pH will increase from perhaps 3 to 7, right? From acidic to neutral, at least non-acidic. So yeah, if you think of it this way, then you will also you start to realize that carbonates can also get rid of the acids. Yeah, so it's the same way, right? So the answer you can see is pretty similar to the alkaline question, the one before. Just that the first thing, we do not use the word neutralize. Okay, over here for the carbonate acid reaction, we do not, I repeat, we do not use the word neutralize because it's reserved strictly for acid alkaline reaction. So you can just say that it reduces the acidity. Yeah, so I'm using the phrase here, reducing the acidity of the content in the stomach. Essentially, it's just getting rid of the acid. All right, so move on. Which is a better choice? Antacids containing hydroxides, the alkaline, or the carbonate. So which one are you going to take? The alkaline version or the carbonate version? And I will say that both work in a similar way to get rid of the acids, right? However, the difference then is that for the carbonate version, you have the carbon dioxide gas. Okay, so if you imagine if you take a lot of this carbonates, and then there might be a buildup of carbon dioxide gas in your stomach that clearly causes bloating. right? And some other discomfort. Yeah, we have discussed this before. Okay, so I'm gonna move on. Okay, of course, the layout of this Word document is different from your worksheet, right? So just bear with it. Okay, the whole idea is that next we're examining this limestone thing, right? So some of you may not know what on earth limestone is. Here you go. Okay, limestone is it can come naturally. You may be able to find limestones naturally. So they come in solid forms, of course, and there are different crystal forms of calcium carbonate, right? Essentially, they are just calcium carbonate. Next time you will learn, right, if you go deeper into material science or chemical sciences, that you can have the same compound, but they exist in different forms, right? Depending on the conditions which they are formed, right? So here, in nature, you see calcium carbonate not in the powdered form that we see, in the lab, right? They can come in huge lumps, particularly crystal form, right? So let's move on here. Okay, so calcium carbonate is actually used in buildings and sculptures and coral reefs, right? You will see the last question concerns the coral reefs, right? So let's move on. Okay. Um, First look at this diagram is quite clear. What is this for? To test for carbon dioxide, right? Test for carbon dioxide. Right. So I might doodle as a student. I might doodle this by the side, just to remind myself. Okay. Cause of lime water. Yeah. Okay. So we know that limestone, this guy here is a carbonate. Okay. In particle, calcium carbonate. Right. And we are reacting it with hydrochloric acid. Okay. Calcium carbonate plus hydrochloric acid. Okay, so move on. What is the name of the salt produced in the reaction? This one is quite simple. You take the metal from the carbonate, so calcium, calcium. Right. The second half of the name, because of hydrochloric acid, this is a chloride. So calcium chloride. Pretty simple. Now, what is the gas produced in the reaction? This one is carbonate plus acid. Right. So it is a salt plus carbon dioxide plus water. So in this case, the gas is the carbon dioxide gas. Pretty straightforward. So how do you know the identity of the gas? Right. Remember when we throw certain things into acid, right, in the lab, right, we see effervescence. We see the appearance of effervescence. But if we don't know what is the substance, like the powder that we throw into the acid, there's no way of telling, by looking, right, what is the identity of the gas, of the effervescence, right, or the bubbles, right? So the only way to test out, um, to figure out the identity of the gas that produced, right? Yeah, do a test, right? We have learned how to test for hydrogen gas. We have learned how to test for carbon dioxide gas. In upper sec, you will learn more how to test for other gases such as carbon dioxide and oxygen, so on and so forth, right? So by knowing what is the gas produced, we can sort of guess what is the solid that we throw in because of the way it reacts with the acid. Okay, so let me just write it down. If we have unknown solid plus acid, and it gives us, well, sometimes we can see the salt because of the color. Sometimes the salt is dissolved in water and giving a transparent solution, plus this gas, right? Well, what is this gas, right? And plus maybe water, maybe, because we can't see whether how much water is produced, maybe. So this one I'm not gonna put it there, right? Water, because we can't really see it, right? So all we know is that, we are likely to get a salt, and we can observe. This is the one that we can observe, right? Observe the formation of effervescence, right? So how do we know the identity of the unknown thing? Well, the only way is you can do a test, right? So if you can figure out what is this gas, then you can tell what is the unknown substance that you put into the acid. All right, so I'm going to erase this. Okay, so moving on. Okay, how do we identify this gas being carbon dioxide gas? So it's asking for, essentially they're asking for the test for carbon dioxide gas. Okay, so bubble through lime water, and you produce the white precipitate. Okay, next. So essentially, yeah, next is just writing down the sorry, writing down the word equation. Yeah. Okay, let's move on. Okay, acid rain is formed when gaseous air pollutants, namely sulfur dioxide. Let me just highlight this: sulfur dioxide and oxides of nitrogen. Okay, now oxides of nitrogen. Some of you may not be familiar with what it means by oxides. Okay, now let me write down the chemical symbol for you, just so that you have some idea, right? Sulfur dioxide is SO2 and it's a gas. Okay, under normal room temperature and pressure conditions, it's a gas, sulfur dioxide. Okay, and oxides of nitrogen. Now realize that there's an S here, oxide. They did not just say nitrogen oxide or nitrogen dioxide. Okay, because it comes in different forms. Sometimes it can be nitrogen oxide, sometimes it can be nitrogen dioxide, NO2. Right? So it really depends. In it depends on what is the conditions, that these oxides are formed. Okay, but typically we are referring to, pardon me, typically we're referring to nitrogen dioxide. Okay, now all these guys, all these molecules are air pollutants. Okay, and they are emitted into the atmosphere. This gas reacts with water vapor in the atmosphere. So these oxides here, sulfur dioxide and nitrogen oxide, they react with water. Okay, so the first question say, name two acids that can be found in acid rain. Oh, hang on, where do this acid even come from? Suddenly there's a mention about acids. Well, if you read the question again from the start, acid rain is formed when these two oxides react with water vapor in the air. So this is how you get the acid. All right. So name the two acids. No, if you, we have not learned how these two gases react with water vapor, or water is essentially to give acid, right? But you can make a guess. Sulfur and nitrogen. What are the types of acids we have learned so far? We have learned sulfuric acid, hydrochloric acid, nitric acid. Anything else? Mainly these three, right? Mainly these three. So we will not, again, we will not test you any old acid that you have not learned. So looking at the name itself, sulfur dioxide, you would be reminded naturally of sulfuric acid, nitrogen oxide, nitric acid. So here we go. Pretty straightforward. So it's a bit of guesswork there. Okay. Okay. Such as how the acid rain could. Oh, by the way, so in case you're curious, how the acids react with the water to give the acid. Sorry, sorry, no, beg your pardon. How do these gases, greenhouse gases, um, no, not even greenhouse gases. How do these air pollutants react with water to give you the acid in the acid rain? Let me just write it down. All right. So we have for the first case sulfur dioxide plus, well, water vapor is just water. Okay, again, you don't need to know this, right? But just for information. Okay, so how does it give you? Now sulfuric acid is H2SO4. All right, yeah. So how do we go about doing this? H2SO4, yeah, essentially is something like this. Okay, next we have the same thing goes for NO2. Okay, it gives you HNO3. Okay, so it goes something like this. This equation, what's wrong with this? This thing here is not balanced. Okay, next time you'll learn that there's a way to, we should actually balance the equation. the chemical equation here, because you can see that there are 4 oxygen here, but there are only 3 oxygens here, right? So you got to figure a way out to, to balance this equation now. Okay, so but that's the idea, right? So when this um air pollutants, these two gases, they either react with the water vapor that's lurking around in the atmosphere, or they are dissolved in the ocean. Okay, they're dissolved in the ocean. They produce acids. Okay, so so how does this affect your limestone structures? Clearly, these are acids reacting with the limestone in the structure. So it's carbonate, right? So this is a limestone here. It's a carbonate. Okay, so acid plus carbonate, yeah. Okay, so the acid reacts with the carbonate present in the structure and corrodes the external surface of the structure over time. You can go and Google some structures that have been corroded by acid rain over time. It's not instant, of course. It takes years after years of acid rain to damage the external. Right. So the features may be not clear anymore. Okay. Interesting fact is that the Statue of Liberty, if you take a look, is greenish in color. It wasn't green in color, when it was first made. I can't remember what's the color. You can Google yourself. Yeah, so it's really due to acid rain that corrodes the surface over time, causing it some. As you can see from the color changes, it suggests that there is a chemical reaction going on at the surface. Yeah. Okay. So what is the gas? Well, carbon dioxide. Clear cut. Okay, so just how the gas formed when acid rain reacts with carbonate, right? When I see limestone structures, I'm in my mind, I'm immediately replacing it with carbonate. Yeah, you know. So how does the acid react with carbonate? How will it affect the environment? So here I'm talking about carbon dioxide gas because because of the previous question, it kind of gives you a hint that it reminds you, right, of how carbon dioxide is produced from this reaction. Henceforth, you can answer by examining how does carbon dioxide itself um, affect the environment. Yeah. So number one, you can talk about global warming itself because carbon dioxide is a greenhouse gas. Okay. The second thing, which is related uh, to the coral reef question at the end. Okay, carbon dioxide is also dissolvable in water. You can see the pattern here. Yeah? Carbon dioxide is CO2, and in the previous part of the question, you have SO2 and NO2. You know, um, reacting with water. Okay, so here you can see that carbon dioxide is also dissolvable in water, or you can also say carbon dioxide reacts with water to produce a weak acid called carbonic acid. For those who are interested, uh, carbonic acid. Okay, carbonic acid, hence producing more acid rain, which can, how does acid rain affect the environment? Well, it can um, affect the pH balance in water bodies such as lakes, so the living organisms inside the lake can be affected also. The pH value of the soil can be affected. Hence, the trees, the other plants will also be affected. Okay, we will learn more of this in upper sec. Okay, um, the increase. Yeah, this is actually it's kind of related. Question 6 and this previous part is related. The increase in CO2 in the atmosphere results in more carbon dioxide in the ocean because, well, carbon dioxide can dissolve in the water in the ocean. So how does this affect the coral reefs? Okay, as we were saying, recall my poor drawing that you have your coral reefs and they have a external structure like their skeleton. Okay, these are essentially a calcium carbonate. Yeah, so these guys are calcium carbonate, calcium carbonate. Right, so do your bones, right? Your bones, they say you must take in calcium to repair bones for bone growth. Yeah, because of this, right? Bones are essentially also calcium carbonate, but they are in different forms. Yeah, same compound, different forms. Okay, so yeah, this part, is not in your notes. I'm not too sure if it's in your textbook, but I think it's expected that you do a bit of internet search here and there. Okay, so as I was saying, it forms carbonic acid when it's dissolved in water. It is a acid anyways, so it will react with the external shell, the skeleton, which is a form of calcium carbonate. And the carbonate, yeah, it will react with the acid, and therefore, um, you know, thinning the skeleton, the shell of these coral reefs. So because of that, yeah, their shell is weaker, their structure is weaker, they're susceptible to damages. Okay, is that all? Now you have one bonus question at the end, which is actually placed at the start of my document here. So why are acids not used in washing agents? Okay, so this washing agents, of course, we're talking about detergents, yeah? Detergent, soap, whatever not, these are alkaline. Okay? So why is it? Why do we use alkaline instead of acids? Well, if you think about this question here, it kind of gives you a hint. You see, we do not use vinegar, which is an acid, to treat bee sting because the bee sting is acidic to begin with. So acid and acid, no reaction, right? So it kind of gives you a hint. Why do we not use acids? Because, well, there might be acids in the food uh, on your dishes, right? Indeed, this the oil and the grease that we consume, they contain fatty acids. Do you remember when did we mention about fatty acids? Yeah, essentially fat, right? Fats in your food, your starch, your proteins, and your fats. These fats are essentially fatty acids. Okay, so they are weakly, very, very, very mildly acidic. Okay, so there you go. You are not gonna use acid to get rid of all these guys. You are gonna use alkaline. So this is reason number one that I can think of because of the fatty acids in the food. Number two I can think of is, well, because of your metal cutleries, right? The metals, actually, yes, the metals. If you're gonna use acid over time, it's gonna corrode the surface of your utensils. Okay, thereby damaging them over time. So not a good idea to use acids. Alright, so that's it for this worksheet here. I hope you can understand what is going on. Even though the last few questions over here might throw you off a bit, but take it as common knowledge, right? Don't be too afraid, you know. Of course, for questions like this, in exams we won't test you because it requires knowledge of carbonic acid. So don't be too worried. At least now you know, right? So yeah, that's it. Please do your corrections, and I will see you again. Take care.